Hi everyone, my name is Jaidev. I'm an applied scientist at Microsoft AI working on the core search team. Today I'll be talking about WebReco, a web page recommendation system at Bing, on behalf of all of my wonderful colleagues and co-authors on this paper. So to set the stage, this is where our product appears. It's on the first page of Bing search results and it appears underneath individual search results that we call URL ones. And so these recommendations are query and user agnostic, aka they only depend on the URL one. And our objective here is not to necessarily answer the narrow query intent, but rather to recommend interesting, relevant, and complementary web pages to the URL one. And so in this example, the URL one is this chinar.net site, and the URL twos are what these recommendations are underneath Explore Further. As you can imagine, for a web scale recommendation system, there are a bunch of challenges. Obviously, one is the index size, hundreds of billions of web pages. There's a latency constraint since we need to appear at the same time as the Bing search results. And then with all things web, there's a big variance in web page quality. You can imagine racy documents, clickbait, and spam web pages. Here's a system overview of our production system. There's several candidate generation paths. I'll go over each of these in detail. There's also a multi-stage and multitask ranking layer, which will be covered in detail too. The triggering model on the top actually decides how many recommendations we want to show. This, unfortunately, we won't have time to cover in today's talk, but it's a very interesting approach, and it's detailed quite nicely in the paper. Candidate generation. So co-clicks or co-occurrence clicks are actually the foundation of our product. When we first started to build WebReco, we wanted a way to use Bing search logs to come up with a strong enough signal to drive recommendation candidate generation. And the idea here is that a co-occurrence click is defined to have occurred when K or more Bing user browsing sessions include a click on both web page A and web page B. These clicks don't need to be consecutive, they just need to be in the same user session. In practice, when you look at the data, what this means is that web page B will commonly represent a frequent destination of the user, post some query reformulations or slight shifts in the user intent. Once we have several months of Bing search logs, we can build a co-click graph where the edge weight is actually the co-occurrence frequency over that time window in which the logs were collected. At serving time, all we're doing is just serving the top 30 URL2s that we've injected into a key value store, ranked on the co-click counts for each URL one. We refresh these co-click counts weekly using the Bing search logs. However, we do want a way to generalize beyond the immediate one-hop neighbors in that co-click graph. Especially, we want to have better performance on body and tail URL ones, which generally don't have a dense neighborhood in the co-click graph because they just don't get enough clicks. And therefore, we take the co-click graph and then we train the URL one and URL two embeddings directly using a CF implementation, collaborative filtering implementation, where we have the embeddings optimized directly using influence loss. There's a loss weight that's a function of the co-click count. We log discount it so that it's not overly helping head URL ones that have the most impressions. And since we only need to do one gradient update on the embeddings, we actually scale to a 2 billion index using a CPU implementation only to distribute a C++ implementation where we train only on CPUs. At serving time, for each URL1 request, we do an init search or a FICE vector index that we build of the item, or aka the URL2 CF embeddings. The takeaway for us was that a simple, well-tuned CF implementation can actually be really strong, but it's also quite sensitive to hyperparameters. And so in table one, you can see that tau, the temperature, and then k, the number of negatives, are quite important to get right in order to have strong performance. We found that our CF implementation not only performs the best on our internal recall evaluation sets, but also on the benchmark data sets used in papers like Simplex or LightGSIN, which are more complicated methods that also require training on GPUs. The two-tower recall path is essentially a two-tower 6-layer XLM Roberta-based transformer model, which are fed the URL1 text features and the URL2 text features, respectively. And by text features, I mean the URL text, the title text, and the snippet text. We trained the model using influence loss. Here, the positives are the clicked URL2s from our production logs where the user dwell time is over a certain threshold. The negatives are a combination of in-batch negatives and ANSI hard negatives that we randomly sample from the top 100 to 300 from ENN search. We build a span index using the URL two-tower embeddings. The index size is around 500 million web pages. And again, at serving time, we do ANN search to retrieve the top 30 candidates. So as you can imagine, there's thousands of fresh web pages being published every second, and we do need our recommendations to be more fresh aware. And so we recently also developed a fresh recall path, but the challenges here were that the span index that the two-tower model uses can't handle index updates at a fast enough rate. And also the fresh documents simply haven't garnered enough impressions to be retrieved by the other recall paths, like for example, CF or CoClick. And so as such, we have a three component process here. So we first developed a fresh intent classifier that classifies a query, incoming query, into whether or not there's some fresh intent. This is trained using a binary cross entropy objective. We use a light GBM here instead of, say, a transformer model because we need the inference speed to be really fast. And so instead of text features, we feed in a whole set of cleverly feature engineered query level features into this light GBM. Things like what's the average document age of web pages in the top K after the penultimate ranking layer of Bing web search, or what are the average Bing ranker scores for the top K documents. And you can imagine there's several of these Bing rankers that are fresh aware and have fresh as a explicit task during training. We then create a fresh disk ANN index. So fresh disk ANN is specifically optimized and supports very fast ingestion and deletion. It's an ANN index of the URL two-tower URL two-tower embeddings from the two-tower model that I described before. And we also now need a way for us to collect a set of which URL ones do we want to trigger on for this fresh recall path. And so this is done using a near real-time streaming pipeline where for each Bing search impression, we classify the incoming query into whether or not it has fresh intent, do the embedding inference from the URL1 tower from the two-tower model, and then we store this URL1 along with the URL1 tower embedding into a key value store. So all of this is done for Bing search impressions, and then at serving time for WebReco for our product, we simply look up the URL1 in a key value store, obtain the URL1 tower embedding, and then do an ANN search with a fresh disk ANN index, obtain up to 30 fresh URL2 candidates that we send to the ranking layer. We also recently launched a LLM-powered candidate generation path called Q-Prime Recall. The motivation here is that LLMs are actually quite good at doing doc-to-query. So given a document text, generating a bunch of queries that explain or are about different aspects of the web page. But obviously we can't serve these online, so we needed a way to generate candidates offline, um, offline for candidate generation. And so the core idea is to obtain up to 5 Q-prime queries for each URL1 web page. For each of the Q primes, we then scrape Bing search to obtain candidate web pages. We then deduplicate across the retrieved candidate web pages and choose the top 30 ranked by a relevance ranker, which is just a cross-encoder model that we've developed. But the challenge here is, whilst this pipeline may support a certain index size, we need really fast offline Q prime generation in order to scale to web scale. So here's a diagram that explains what I've just described, but I'll now talk about the scaling. And so what we first launched was a 100 million URL1 index using GPT-4 for Q prime generation. And we saw that this is very strong online CTR and Reco DCG gains. Reco DCG is a quality metric I'll talk about later. However, GPT-4 actually is really expensive and it is not suitable for scaling to a, say, billion or 2 billion size index. So our next step after this was to take GPT-4 generated Q prime queries to supervised fine-tuning to slow down to a Mistral 7B model. And whilst doing this, we actually were able to achieve parity in Q prime generation quality, but we increased our inference throughput by over 60 times on the same hardware. What this meant was we were able to scale to a 600 million URL1 index at a fraction of the compute cost and time. Here are some examples of generated GPT-4 Q-prime queries and then the Mistral 7B Q-prime queries for a web page. In this case, the web page is Adele's YouTube video, hello. For each of the Q-prime queries, we scrape Bing and we obtain candidate web pages, which we then deduplicate and re-rank and get the top 30. And so on the table on the right, you see the candidate recommendations that are generated through this offline process. All right, so let's go to ranking. After all of these recall paths generate candidates, we do deduplication. We send around 200 URLs or URL2s to be specific to the ranking layer. Before I get into the specifics, I do want to first point out that for quite a while we faced quality concerns. So since we've trained historically our entire system to be optimized towards clicks and click logs, we found sort of a proliferation of low relevance, clickbait, low authority, and spam content. So here are some examples of user feedback submitted where the recommendations are not up to par. And so to solve this, we introduced quality as a separate task during ranking. So here is the three-stage ranking layer. There's the stage one, which is a light GBM ranker that has a whole bunch of inexpensive counting features. Counting features are essentially click and impression counts on at different time windows and aggregation layers, which I'll talk about in one of the next slides. After the stage one ranker, there's a cross-encoder model that has two tasks. There's a click prediction task that's trained using pairwise loss, and the recommendation quality task, which is a classification task into one of several quality classes. The cross-encoder model scores, along with a whole bunch of other features, including the counting features, are then fed to another light GBM ranker that is trained using lambda rank. And this is trained towards, again, click prediction. At stage three, we do a linear combination between the stage two light GBM ranker click score and then the WebReco LM, which is the cross-encoder model, its quality head score. And this gives us a trade-off between clicks and quality. And at the final stage, we do host deduplication. So we want to make sure we don't just recommend web pages from the same domain. We have a whole set of adult and spam filters. Counting features are clicks, quickbacks. Quickback is when a user goes to the web page and then quickly comes back, indicating he wasn't satisfied. And impression counts across 3 time windows and 5 positions. And so these can be features like what is the click count for a URL1 and URL2 across the last 7 days at position 0? What is the URL1 aggregated click count across the last 168 days at position 3? And all sorts of variants of these features. So we have a daily refresh pipeline that generates these click count and impression count and quick back count features, and these are served through the LightGBM rankers through a key value store. I'll now briefly talk about Reco DCG. This is our internal recommendation quality metric. As we all know, human relevance labeling is quite expensive, it's inconsistent, and it's too slow for experiment agility. And last year, we developed a pointwise LLM-powered offline quality metric, where its goal is to measure the recommendation quality of URL2 as a web page recommendation for URL1, but it does this whilst reasoning across different aspects of what's a good recommendation, things like relevance, freshness, authoritativeness of the domain, and location appropriateness. And we use this quality metric to not only make control versus treatment shipping decisions, but also we use the recommendation quality labels to make our ranking stack quality aware. So that's what I'll talk about in the next slide. RecoLM is the multitask cross-encoder that I mentioned in the system overview. The base model is pre-trained on billions of Bing search logs using a mass language modeling objective, but also pairwise objectives for predicting dwell time and URL position. For this base model that we use for the teacher, we have both the click teacher and the quality teacher, where the click teacher is trained towards pairwise loss using the log dwell times. And then the quality teacher has a classification task across the 5 quality classes, 0 to 4, where the labels come from the recognition quality prompt that I talked about in the previous slide, the Reco DCG recognition quality prompt. We inference around 30 million URL1, URL2 pairs along with the quality scores, and then we train this quality teacher. And we distill down to a student model that's only 6 layers. It's a mini LM-based model where the feature input is the URL1 text features followed by the URL2 text features. And we distill down across these two heads using MSC loss. So quick prediction head and the quality classification head. Here are some quick ablations. We found that pairwise softmax loss does quite well. Distillation is really important. You can see in the table below the gap between the quality head in the teacher distillation case versus direct fine-tuning case is quite large. So here's some quick takeaways. Firstly, light GBM rankers are really strong, especially when you have a layered system where there's a cross encoder model that takes text features and then the light GBM that can take all of your counting features and numerical features. This offers a very strong ranking baseline, and we've tried to replace this by other more state-of-the-art models, but this is already really competitive. Secondly, simple but well-tuned models are critical to achieve web scale. Click-based metrics and quality are often misaligned, and so shipping this requires careful analysis of logs and knowing what clicks exactly are you losing. LLMs provide a very powerful way to bake product objectives into a metric. So this is the WebReco DCG metric that we detail in our paper. But they also provide a strong signal to enhance both retrieval and ranking. And lastly, this is in reference to the LLM-powered candidate generation. Not only are we doing this, but I've recently seen this as a trend across several industry recommendation systems. And whilst deploying LLMs online are still a while away, LLMs are already today enabling a whole wave of clever ways to enhance retrieval. But a lot of the computation will be offline in the foreseeable future. Thank you. I'm happy to take any questions over email or LinkedIn. And here again is a QR code to the paper.